One of the things that we're going to start talking about in this class and with these set of examples is something called recursion. So you should have heard about recursion in your previous computer science class, but if you don't remember, recursion is when a method calls itself. So, for example, you have some method that might be, might look like static, return maybe an int, we'll call it foo, you might receive some parameters. Then somewhere in here, we're going to call foo with another set of parameters or arguments where it is self-referential. Okay? So the nice thing about recursion is that it's very easy to represent a lot of mathematical formulas and structures with recursion. So one of the things like we're going to do is prove, or not prove, but show that a lot of different simple math operations can be represented with recursion. We're going to do this with the assumption that the inputs to these methods are all natural numbers, which are numbers greater than or equal to 0. So let's assume that we only have access to 3 methods. We have one for add 1, which adds 1 to a natural number. We have another for subtracting 1 from a natural number. Then we have one for returning whether a given natural number is 0 or not. Okay? So we want to write addition, or we want to know how to add 2 numbers using what's called natural recursion. Okay? So let's think about how to do this mathematically before we jump into doing it with programming. So let's say we want to add the numbers 4 plus 3, and I'm going to use a different color to represent the recursive operation here. Okay? So hopefully you'll agree that this is the same thing as 3 plus 3 plus 1. Okay? These are the same thing, right? Now, hopefully you also agree that this is the same thing as 2 plus 3 plus 1 plus 1. Okay? Right? So let's continue simplifying this. We'll make this a little bit bigger. Hopefully you agree that 1 plus 3 plus 1 plus 1 plus 1 is the same as 0, 3, 1, 1, 1, 1. I'm using the orange color to represent the recursion here. Okay? So when we have a recursive problem, we're trying to break it down into something called its base case. The base case of a recursive problem, as you might know, is when the problem can no longer or can be subdivided no further or broken down no further. So with natural numbers, hopefully you remember that the identity element over natural numbers in addition is 0. Now what does all that mean? That just means that 0 plus m, or let's be consistent with the color here, 0 plus m equals m for any natural number m. Okay? So that means that we can actually simplify this portion here to what? We can simplify that to just 3. Okay? And we still have all of these plus 1s over here, so let's just copy those to make it a little bit easier. And now we can just resolve these from the inside out. Okay? Or from left to right even. So 3 plus 1 is 4 plus 1 plus 1 plus 1. Okay? And 4 plus 1 is 5 plus 1 plus 1. And 5 plus 1 is 6 plus 1, and that is 7. Therefore, we have shown that 4 plus 3 is in fact equal to 7. Okay? Now, the actual addition here isn't really what's exciting. What's exciting here is the fact that we've done this recursively. We broke this down via a series of recursive calls. Okay? This plus here represents the what I'm going to call the add method. Okay, and it receives two inputs, N and M. Okay, and it breaks N down to the base case. We know that the base case could be 0 plus M is 0. Okay, so we could do a case analysis, an if statement on N, and when N is 0, just return M. Okay, otherwise we would break down the first argument, N, to be 1 less than its current value, right? And then outside of that, we're going to do these plus 1s. Now, what do all of these correspond to? The plus 1, in fact, corresponds to add 1. The minus 1 here corresponds to sub 1. And then each time we decide to either break the problem down or use this identity relation, we're using is 0. Right? So now let's see what this looks like in code. Okay, so we've written the documentation, we've written the test cases, this is sufficient. Now, what did we say we're going to do? We're going to first have a case analysis that says if N is equal to 0, and we're going to use the methods here. If N is 0, what do we do? Well, what did the diagram say? We're going to return M. Okay, that's what this identity relationship here tells us to do. Okay, so our base case is when N is 0, so we return M. Otherwise, we're going to return, and we're going to make a recursive call in here somewhere. And there might be some stuff that we need to do after this, so we're going to put some dots around it to serve as a sort of template. Okay? Now, what do we do in between each recursive call? How does N change and how does M change? M stays the same, so we can just put M as the second argument. Now, how does N change? N changes by subtracting 1. Right? So, we can just call sub 1 of N. Now, the stuff outside of this, we have a plus 1, right? So that corresponds to an add 1 on the outside. Okay? Now that we have that, let's see if our tests pass. And they don't. So, was not expecting this, actually. This was not planned. Let's see, which one failed? Oh, that's because, 0 plus 3 is not 1. It is 3. Okay. So this is an example of sometimes when your test case is wrong. Alright. But that is the test cases. They all pass. But now let's trace this through and see what happens. So let's see. So if we call add with 4 and 3, that's going to be the same as doing a case analysis on N. So is N 0? No, it's not. We're going to break that down into an add 1 of add of sub 1 of N, where N is now 3, and then this is 3. Now this is going to be broken down into another case analysis. So is N equal to 3? No, it's not. So this becomes add 1 of add 1. So we can take this whole thing and then wrap it in a call to add 1, where this becomes this. Then we take this. So is N equal to 1? No, it's not. So we're going to wrap an add 1 call around the recursion. This becomes that. We do it one more time. Add 1 of this. Now here, this just reduces to M because N is 0. Right? So then this whole thing becomes just 3. Okay? Now we have an add 1 of 3, which just becomes a 4. And then this whole thing just becomes a 5. Then this whole thing becomes a 6. And then this finally becomes a 7. Okay? So we break down the recursive problem, we reach the base case, and then we unwind the recursion. That's what this step is called. So this is unwinding the recursion. Okay, that's very sloppy, but unwinding the recursion. Okay? Alright.